Okay, now and there's the green, there's the dot. All right. So, but I think I'm going to kind of review a smidgen and then go forward. And I wanted to talk about integrating that delta function. And really, it's almost given, or it's just by definition, that is just a property of it, right? And that if I were to do something like this, it's just a given that that's going to be that, right? But that might not satisfy you as much. So kind of what you have to do to understand a delta function is actually do an approximation to the delta function. Sorry, all right. And I'm just going to give an example here. The time, the width is 100th, and it's 100 units tall, right? And that means the area is going to be equal to 1, right? Now, I don't like that color. All right. So I just drew this box, but we actually have in our step function, we can actually formally do that with step functions where we have 100 times the step minus another step delayed by 100th. All right. So now we can actually integrate this, right?
Time seemed to slow down as his eyes locked on mine and opened wide. He's raised his fist into a quintessential guard. I was game to play alone with him, to act as if I was a worthy opponent. What an honor to be.
Sorry, guys, I had to mute you all. All right, but I think if you press the space bar, you can. All right. Well, what I want to do now is do it with time, right? I'm going to bring out the 100. Then I'm going to have u of tau, right, minus u of, no. This isn't convolution just yet, all right? All right. So we have our integration variable tau, right? And I can break this up into two functions, right? So I'm going to have 100. And I'm just going to quickly, right? If I start integrating at 0, then this just becomes 1, right? Now integrating at 0 here doesn't do you much, right? Because it's delayed. So you actually change the limit to this delay. And now I don't have to worry about anything in here. It's just 1. All right. Well, now what I get, and now, yeah, when I integrate 1, I get tau. I evaluate it at 0 and t. I get t. I'm going to leave a space. And then here, right, I'm at tau, and I have my limit of t, and then the other limit of minus 100. So I get t minus that delay, right? Now, remember, these were all step functions to begin with. So there's nothing to integrate before t equals 0. And so I have to remember that since I started here at 0, I have to put a step function that activates at 0. Oh, yeah, sorry. Okay. Yeah. Okay, thanks. All right. And then here I have to put u t minus 100. And I'm running a little bit out of space, so I'm going to, all right. So now we have 100 times u t. Dude, I'm teaching, man. Okay, minus ut minus 100th, or delayed by 100, right? T divided by 100. All right, which I like to put in like ramp format. All right. Okay, so now what that is we have 100 here minus RT delayed by 100. All right. Now, what does that look like in time? Is that we have this ramp function, nothing. Then we start ramping, but our slope is 100, right? And then the other ramp function is pointing in the other direction, or we have an opposite slope, right? And its slope is minus 100, right? Because we're scaling that. But really, I can take the 100 aside, right? And just notice that, oh, I have a +1, and then I have a -1, so it'll just flatten out, right? And then if I went over by 100th, right? So if my delta time was 100th, scale by 100, well, it's 1. All right. Now what I'm going to say is, let's call this like dt, right? And then this scale factor, right? I'm just going to be 1 over dt. And then if we let this scale this time get smaller and smaller, right? So if, let's say it was 1,000th, Well, I'd only go up to here. I mean, I'm trying to draw 1,000th, maybe not successfully, right? So that's where it flattens out, but now I'm multiplying everything by 1,000. So it flattens out that much sooner. And if I let this time go to 0, this goes to infinity, and you get the step function. And let's just right. I'm going to call that dt, and this 1 over dt, right? The area is still 1. So and that's how, since this is time, right? So without a definition of a step function, you can, the delta function, you can use a simple rectangle and then let the width go to 0 and the height go to infinity. And you can see how this shape gets sharper and sharper and sharper till you actually get the step function, all right? Now, oops. So let's call that h, where we just have a series of pulses, right? And then let's make g ut, all right? So then if we want to find the convolution of that, all right. Well, let's do it intuitively first. And the thing is in this case, I've said this is h, right? But I'm actually going to flip and drag g, because it doesn't really matter which one, you know, g tau h t minus tau d tau, or g t minus tau h tau d tau. It doesn't matter, right? And so I'm pulling this through as we're integrating, right? Well, this area, when you integrate that area, it's 1, right? And it stays 1 in time, right? When we're just doing a finite integral, you just get 1. But if we come back here, as we're integrating, right, over this shape, the area goes up to 1. There's no negative area, right? So it doesn't go back down, all right? Which is why it turns into a step. And then, so really, I wouldn't even set up the integral here, is that I know that, like, what's the simple thing of delta t convolved with anything equals anything, right? Now, alls we have, though, are the delta functions haven't been scaled. It's all by one, right? So only we have is these delayed things. So so in this case, in this example here, that convolution is going to be, right, since we have a ut convolved with a delta, we have a ut. And then we just scale each one. All the way to 4. All right. And if I were to plot this, right, I get a staircase function. And yeah, if I start putting negative delta functions, well, then I start getting negative areas and I can start going down. But way too, yes.
Shouldn't those be pluses, not minus,
Where?
for the step functions? Shouldn't they be added to each other instead of subtracting from each other?
I'm not even going to bother to say I meant to do that to see if you guys were awake. Sorry. Yeah, no, we're adding. Okay, I don't know where that came from. Thank you. So now, notice how the step is 1. Now, if I say, all right, here's this dt in between, right? But now I'm also going to multiply this by dt, right? So this would be dt, this would be 2 dt, 3 dt, and then the whole thing is scaled by that time. Well, what happens, this gets closer and closer, but you step up just a little bit less, and as dt goes to 0, right, and as dt goes to 0, rather than these boxes, right, you get a ramp. And that, it's kind of like where 112, you know, 112, 110, you know, we're kind of talking about very similar things, all right? Now, sometimes I ask, you know, on exams, things with the delta function, and really, I showed you how to integrate a delta function, but it's best just to have that identity that anything convolved with a delta function is that function. And if it's convolved with a delta function that's scaled and delayed, then you get that function that's scaled and delayed. All right. All right, the Laplace transform, right? we're finding a function in S. What's S? It's something that's real plus something that's imaginary. All right. And we have a two-dimensional plane, right? So we take a function, right? And it's got to be linear and time invariant. Otherwise, it's meaningless, right? But we take a function in time, right? Something, right? And then we convert it into a function that has the real and the imaginary part to it. And it's in units of frequency, all right? So we go from something in seconds to units in frequency. And the whole point is that this symbol in time becomes this in S. All right. So we have this is a whole convolution integral, right? G tau times ht minus tau d tau, right? Where here we would just have, I'm using capital letters, G of H times H of Ace. H of S, right? And J omega, it's J, right, J omega, it's, okay? Now, sure, right? If I give you two functions in time, you have to convert it to the frequency domain. And then to get back to time, you have to unconvert it, right? But that, sometimes it's just a lot easier to do it that way. And we're going to find out that it's actually better to start in the frequency domain, which then you can describe your system and how it's going to behave. You can design it, analyze it, and then if you have to, you go back into the time domain. All right. Now let's just do all right. So we're not, I mean, we're finding it all in a function of S, right? So it's not, we're not creating a function of T, we're creating a function of S. Oh yeah. You know what? Yeah, no, yeah. Because the minus sign is here. All right, my bad. Thanks. Thanks, Kevin. All right. So remember, in this case, we're starting at 0. And what that means, and I can show you some examples, but that means these things start at 0. It's not like the Fourier transform where they kind of always exist. All right, and that has some. So really, if I'm starting at 0, I can just make that 1. Right? And you can do others, right? But really, you would have done a few of these in differential equations, or if you feel that you need to find other ones, go ahead. But really, we tend to just use the tables as given, right? And while there's an inverse Laplace transform, if you read the book carefully, they'll tell you that what you do is you find the Laplace transform, which then becomes the inverse Laplace transform. And you kind of, if you're looking for an inverse, you might try guessing, create things that will create that, because it is actually really hard to do the inverse Laplace transform. All right. So now we know that the Laplace transform of ut equals 1 over s. All right. And the scaling in time I'm adding that is okay. And what you'll find is that, well, we'll do, when we do the example, you'll see. All right. All right. So now let's do the convolution of ut and ut. And it's going to be the inverse Laplace transform, right, of the Laplace transform of ut times the Laplace transform of ut. Let's see, got that right. And I'm just gonna, which we just found the Laplace transform of the step. Now, so if you look at the table, right, 1 over s squared, the inverse Laplace transform of that is t. However, right, this whole thing started at 0. So you have to put the step function back or it won't work. All right. Now, All right, so I want to make a step function, and that is what, 0.5 times So this is a quick and dirty step function, all right? It's a little bit rounded, but what'll happen is if I do u equals okay, that you see how it doesn't plot it always, like it jumps discontinuously, which it is, but it just doesn't make for a satisfying plot. So I tend to use that. Where were we? All right. Desmos has a weird, tau is a pre-assigned variable, right? So it doesn't like it. When you use tau. Okay. And there's the convolution integral, right? Done in linear format, right? I can also come up with RT equals T times OT, right? And then oh, there we go. And you can see that I delete it, right? And I can scale it and things like that. All right. Now, of course, that's a great way to check your work. But in this case, I want to convolve this sine wave with a decaying exponential. And I get this. Now, this was a little bit more than what I'm prepared to explain today, all right? But you can see that it doesn't exist, and then it takes time for it to settle, all right? and this is actually a filter, and the lower the frequency, the more of it gets through as we're getting closer and closer to 1. Whereas I lower the frequency even more. And yeah, this is going to be in the lab manual come Friday, where I'm showing you how to use symbolic math to do this kind of thing. All right. Now, we talked about convolutions, right, with ramps. And yeah, just in case you missed the email, I think I never really did ramp times ramp in class, but if you look at the convolution warm-up homework question 11, there's a button called detailed solution, and it'll show you how to do it, but with different numbers. All right. Now, the thing is we've talked about, we have a system, right? And we put in a signal, right? And we get a response. And one such system is an RC circuit. Which, you know, you should have been shown in differential equations, all right? And you would have solved it all in the time domain. Now, if you look on page 36 of the text, there's there's 11 equations, right? It takes to come up with the impulse response of that circuit, all right? And so the impulse response is, if I put in a delta function, well, then I get h of t. And so it's the fundamental description of a system. Now, the real power, like of the S domain, right, is the fact that, again, calculus, so like calculus, so things like integration actually become 1 over S, and things like taking the derivative become S, and so calculus becomes algebra, right? And we can continue to use everything that we ever learned about resistors, right? So if I have 2 resistors here, well, you'd use voltage division to find that output. But when I say, well, the current is the capacitance times dV dt, and well, wait, how do I do voltage division on that? Now, yeah, that current is the same everywhere, and the voltage drops have to sum up, but That's just too hard. And even though in the book they came up with they derived it, and you can do it for an RLC circuit as well, but anything more complicated than that, and it's just really hard. Okay, so now what I'm going to do is say, oh, the impedance of a capacitor is 1 over SC. The impedance of a resistor is just the resistance, right? And my input can be a delta function, right? Which the Laplace of that is just 1. It can be a step function, and the Laplace of that is 1 over S. You can have a ramp function come in, and the Laplace of that is 1 over S squared. All right. So with the Laplace transform and impedance and having everything in the frequency or the S plane, I can use voltage division here, right? So V2 will equal V1 times ZC, ZR plus ZC, right? Now this equation it's correct, but you really want it in a proper format so that you can do the inverse more easily. And what you do is you multiply through by S and you remove the R. So you get 1 over RC. All right. Now, I want to find the impulse response. All right. Well, we're in the Laplace domain, right? The convolution of this and the ultimate HT that we're trying to find in the Laplace domain is really 1 times okay. Now again, this is in terms of S. Is that L? ZC equals 1 over SC. Is that what you're? No, these are arrows, not equals. Okay. Sorry. So now to find H of T, that's the inverse Laplace of this. And when you look up the table, you get this. All right. So that means H of T, all right, 1 over RC, E to minus T, RC. Now, what if I want to know the step function? Well, if I want the step response, right, that would be ut convolved with ht, right? And, right, the step function becomes 1. This becomes 1 over RC e to the minus t minus tau d tau. And you would evaluate that, right? The Laplace transform method, okay, the ut is 1 now because I'm starting at 0, okay? Or if you, yeah, back here, right. You should put a ut there to enforce the proper condition. If that's what you meant, Rudy. Yeah, you're totally right. All right, let's do this in the Laplace domain. Ut, right, that becomes 1 over s. This becomes okay. Now, what I have to now I have this in the S plane, right? I have to take the inverse Laplace of it, right? And the thing is this may or may not come up. Not every integration table has this, but the one that I use does. All right, and what we get is 1 minus e to the minus t RC remembering to put the sorry, that's the tau. Okay. All right. All right, so this is the impulse response. But notice I forgot to put the ut here, and so it keeps increasing as time gets more negative. So I have to put that there. All right. Now, it doesn't quite go to 1, and there's a kind of a rounding, so I can make the tangent function operate a little bit faster. But here's the important thing, right? it effectively goes to 0 in 5, right? Because right now, tau is 1, right? And if I play this animation, right? All right. As tau goes out to 10, well, it takes 5 times 10 to go to 0. And as it goes to 1, all right, okay, it gets sharper and sharper, takes longer and longer, all right? But it's a first order decaying system, and it takes approximately 5 time constants to go to 0. All right. Now, if we wanted the step response, right, I have that. All right. Now, this is something we call, h of t equals, all right, in the frequency domain, or the S-plane, we have that because we're taking it out off of node 2. All right. Now, what if we had this? All right. Now, there's more than one way to do this. All right. But if we look at the voltage division here, right, V2 over V1, right, will equal R. All right, so we get this. And if I wanted the step, well, actually, so if I want the impulse of that, right, I need to take the inverse Laplace transform of that transfer function, right, which is more than likely not on the transform table. And so you have to use partial fraction expansion to get okay, which becomes now the delta function doesn't really need a UT, but it, you know, it doesn't hurt it. But the decaying exponential does. All right. And that's probably the simplest way to find the impulse response of, this is called a high pass filter. And this is called a low pass filter. All right. And let's see. Okay. If I want to find the step response of that, sure, I could convolve a step function with this and find it, but it really is a lot easier to do it in the Laplace domain. So we had S plus 1 over RC. All right, we want the step function. So V out step, right? Well, multiply the step in the S plane. All right, oops. Okay. We take the inverse now of this function. Again, you have to put in the UT there. All right. So remember, we're convolving this step function with, I mean, what this is the step function convolved with the high pass filter, and it detects this edge. See, it goes to 1 instantaneously because that's where the edge is, right? And high pass filters detect edges, low pass filters smooth edges out. Now it still takes 5 tau after it's detected the edge to dissipate, right? And yeah, I can make it respond quickly or more slowly, but it's that's how that that high pass versus low pass. Now there is a So this is the step response, right? And if I want to find the impulse response from that, I would take the derivative, right? So I get minus 1 over RC e to the minus t RC ut. But if you then try to integrate this to get back here, it won't work, because that initial condition kind of set out by that delta function, right? It's missing. And so that can lead to some confusion, right? Where if you just start it in, keep it in the S plane as long as you can and then convert back, it'll avoid that. Okay, what did I mean by an edge? Yeah, so right here, it's an edge. The edge has a finite slope. Right here, I'm trying to draw an edge with infinite slope. But rather than kind of integrate this whole thing, I'm actually taking the derivative, right? And so wherever that happens in time is where the edge was in time. So let's say that edge comes at 2, and I detect it, right? I have 2, and then it decays. Here, right, it will kind of detect it, right? Where on a step function, if I convolve this with a step function or I integrate it, right, no area, and then the area will increase linearly. And so the thing is this 1 over S, it's actually like the integration operator, and S is a derivative operator. And people will throw those terms around almost interchangeably. Okay. But let's see.
Professor,
Yep.
do you mind extending the due date for the Bodhi plots? Is due September 6th.
That's not right. That's not an extension. I just have to fix it. Sorry about that.
Okay. Also, I was gonna ask if you could like make a short little video and just post it on YouTube or something, so we could have a deeper understanding of what you want off of Bodhi plots. Or should we wait till your lecture?
You emailed me before, right?
Yes.
Yeah. It's just that quick little video doesn't exist yet. And I know you want to get ahead, and I want to support that, but sometimes I'm kind of in a triage situation. But
Okay,
I'll see what I can do.
okay. Thank you.
Now, okay. So here, right, I just wanted to say that I can't necessarily do every problem, right? But here I have some worked out time domain convolutions with plots. Okay. And it's all in Python. Now you could download that Python code. Unfortunately, it's all in 2.7 or Python 2 version, not Python 3. And it might not run. It's usually a print command that dies. Okay. But you know, every single one, even this, you know, we kind of did today, it's there. Sometimes it's even color coded. This one's really hard. Okay. Let's just say, all right. But yeah, Desmos is great, but the way I can color code each part of the curve to correspond to something. So for scientific plotting and things like that, you know, Python, I think, wins. Although there are people who I think they do use GeoGebra and some other things for that. Okay. And I think after this week's lab, should be better. Okay. But yeah, right. So we got to talk about Bode plots, which takes some time. But no, it's not due the 6th. It should have bumped it because, yeah, no, that doesn't work because, anyway, I'll fix that. No, it's it's not an extension. But homework, right? The 3 and 4 should be due this weekend, right? You have everything to do that. Okay. All right. Hey, you gotta go. Oh, I have to go too. All right. Take care. And yes, you can email. Better to email sooner than later. Okay. All right. Take care.